Good morning everyone. Today I am here to explain on single carrier communication systems using open source embedded platform. This presentation includes introduction, methodology, results, conclusion, reference and acknowledgement. Initially, when we consider about single carrier communication, it's a data stream multi-level signal which is multiplied with single carrier in order to get a modulated signal. There are many possible modulation schemes. Some of them are binary phase shift keying, quadrature phase shift keying, and quadrature amplitude modulation. A software radio is a communication where we implement the software components like voltage control oscillator, modulator, demodulator, detectors, and so on in means of software using embedded system as computer. The benefits of the embedded systems are it's more cost effective comparing to the multi-carrier signal, also the short duration simple with broadband signal. It's a simple way of implementing, and the spectral efficiency is very small since it utilizes the bandwidth. Also it takes very less memory to implement, and timing synchronization takes less memory. And in the methodology, initially the transmitter was constructed. The transmitter converted the binary bit stream into baseband carrier modulated signal. Initially, the binary data is converted into real and imaginary parts. The real and imaginary parts are modulated, and the modulated signals is gone into the pulse shaping to utilize the bandwidth, and the baseband single carrier signal is produced, and further this could be developed for radio frequency up conversion. This shows the pulse shaping, where the modulated signal with single carrier is multiplied with the Gaussian pulse in order to get the pulse shaped signal. And at the receiver, the modulator is demodulated and filtered in order to get the output signal. At the front end, analog signal is converted into digital form, and then carrier recovery is done. To feed into the Gardner's algorithm, 3 samples are taken per symbol, and it's filtered using match filter, and the data bit stream is obtained. And here the Costas loop is used to eliminate the carrier error during the signal transmission. Initially, the received signal is multiplied with the voltage control oscillator signal, and it's sent to the match filtering for filtering, and both the top part and the bottom part both are multiplied together, and the error signal is filtered for smoothing, and the DC value controls the voltage control oscillator. Likewise, the QPSK also is like BPSK, but it includes a slice and extract. The first equation shows the input signal, second equation is for the carrier frequency offset, and third shows the error signal. In timing recovery, ideally, both the transmitter and receiver should have ideally the same clock frequency, but in real, it differs, so that it causes the timing error. By using certain algorithms, this timing error could be utilized. The modulated signal is converted into digital signal, and the carrier recovery is done. To get 3 samples per symbol, it's downsampled and fed into the Gardner's algorithm for timing recovery. And PI controller smoothens the error value, and according to the error value, the voltage control oscillator controls the sampling frequency. This shows the Gardner's algorithm. The first one shows the correct timing, where the error value is 0. The second shows the timing late. The error value is a positive value, and the third one, the timing is early, so the error value will be a minus value. As a result, in timing recovery, initially a pulse train was checked. The pulse train was fed into the match filter, and it was filtered, and then the match filter signal was transmitted to digital signal, and it was downsampled to get 3 samples per symbol and fed into the Gardner's algorithm. The error signal was fed into the loop filter in order to smoothen the signal, and the smooth digital value control the oscillation frequency. This was the model which was implemented in MATLAB Simulink, and this was the waveform output. And this is the Simulink model for the BPSK carrier recovery signal, and this shows the output of the BPSK carrier recovered signal. At the same way, QPSK was also implemented, and this is the real part of the QPSK signal, and this is the imaginary part of the signal. After implementing both carrier recovery and timing recovery, both of the signals were integrated in order to get the BPSK complete modulated signal. In that modulated signal was fed into the sample and hold, and it was converted to digital, and the carrier recovery was performed, and demodulated signal was obtained. From the demodulated signal, it was downsampled to get 3 samples per symbol and fed into the Gardner's algorithm, and the loop filter smoothens the error, and the smooth DC value has controlled the voltage control oscillator, where the sampling frequency is controlled. And this is the MATLAB Simulink for the BPSK model, and this is the timing recovery for BPSK, and this is the carrier recovery for BPSK. Likewise, the BPSK, QPSK also includes the same components, but in addition, it has a slicer in it. And this is for the QPSK model. And the real part of the signal is shown on the diagram. And this shows the imaginary part. And this is the timing recovered signal. And for the QPSK, when we recover one side of the signal, either it can be imaginary or real, the whole system gets utilized with the timing recovery. In conclusion, I would like to say that this project has proven the feasibility of implementing single carrier communications on radio embedded hardware. Also, we have implemented BPSK and QPSK modulation schemes. Also, is a very low cost effective way of implementing. This could be used for early warning systems, Internet of Things, and sensor networks. And this could be further developed for voice communication, satellite communication, and terrestrial voice. And these are the references that I referred. And I would like to thank each and every individual who has made this project a success. Thank you.
The subject is open for discussion.
How do you intend to solve the problem of timing jitter, which make errors in your system, which could make errors in your system?
There are many algorithms for recovering the time. Some of them are Reed-Moore algorithm and Gardner's algorithm. Here I have used Gardner's algorithm. I have taken 3 samples from a symbol and have fed it to the Gardner's algorithm and got the error signal, and the error signal has controlled the voltage control oscillator, which controls the frequency, sampling frequency.
Was it just a simulation or did you implement this as a hardware?
Yeah, this was initially implemented in MATLAB simulation, and then it was implemented in a microcontroller as well.
The result you showed was simulations.
Yeah, simulation.
So in the microcontroller implementation, how do you implement the actual transmitter? Like are you transmitting into the open air?
No, it was a wired communication. Like initially, just for the testing purpose, we did the microcontroller.
Yeah, that's what now. Did you implement it in transmitter also? Like
Yeah, both the transmitter and receiver both were implemented.
in open air transmission or wide?
Bind.
Wide.
Yeah.
So in actual implementation, you implemented for BPSK, QPSK.
In actual implementation, it was only implemented for BPSK signals. Yeah. But it was tested for the BPSK and QPSK in Simulink model.
So So what were the bit error rate figures were?
Yeah, the errors like timing, it was mainly focused on timing error.
I'm talking of the bit error rates, BER.
Yeah, bit error rates, actually the bit error rate was not considered in this implementation. Only we implemented to test the timing and carrier recovery.
But the intended applications were Internet of Things, and so you require the bit error rates.
Yeah. This should be further developed, but this was just like a prototype.
This prototype finally will it be a wired, sorry, not prototype, will it actually implement it, will it be wired or will it be through the air?
It can be both, like even we can implement in the wired or wireless, like for the satellite communications also this could be further developed.
How about the other implementations? Did you conduct a liquid survey and such, like to check how others have done this? So, any other implementations, civil implementations?
Actually, we went through everything, but unfortunately the implementation was not there for the timing and carrier, like in the software, mainly the software platform. It was implemented initially, like earlier, in hardware components, using hardware components. This was mainly focused for the cost reduction.
Any more questions? Any more questions? In the absence of any more questions, let us show our appreciation in the usual manner.